Hello everyone, I'm Zhou from Tsinghua University. Today, I'd like to introduce our work titled SatAOI, Delimitation Area of Interest for Swimming Arm Traveling Robot for Construction. First of all, let's talk about the opportunities of traveling robots. With the development of automation technology, construction robots are transforming traditional construction methods. Concrete floor traveling, in particular, is a monotonic and repetitive task with high precision requirements. Traditionally, it requires plenty of workers to operate travails over large surface multiple times, which is time-consuming and labor-intensive. However, using traveling robots brings significant improvements. They can enhance efficiency by 3 to 5 times, reduce the workload by 60%, and ensure concrete surface with a consistent flatness of 3 to 4 millimeters. But there are challenges. Construction sites are often filled with obstacles and holes, featuring a variable and unstructured environment. This poses great difficulties for the automation of construction robots, resulting in low automation levels for traveling robots, which really highly rely on the participation of skilled workers, such as human-robot collaboration or complex predefined paths. Furthermore, the essence of traveling work lies in coverage path planning within a specific scene. That is, to find a collision-free trajectory to ensure the robot fully covers an area of interest. So the first step is delimiting AOI of given region, which is to determine the area can be traveled. Path planning is the next task on the basis of AOI. Therefore, delimiting AOI is a primary and critical part for the automation of traveling robots. Moreover, since the complex degrees of freedom of swimming arm robots, the passability and workability among obstacles presents a huge challenges to AOI delimitation. So, our objective is proposing an AOI delimitation algorithm for swimming arm traveling robots to improve traveling automation level, which we call the SatAOI algorithm, a wish for robots working on Saturday. Our research contents include establishing mathematical models for swimming arm traveling robots and obstacle maps, then proposing the SatAOI algorithm suitable for construction scenes, and validating its effectiveness through a case study in different complexity scenes. Now, let's step into our methodology. The overall framework includes 3 steps: building the obstacle map model, constructing the robot model, and developing the SatAOI algorithm to search for areas can be traveled. Firstly, for the obstacle map model, we extract obstacle information from beam models or CD joins. These digital assets contain rich building semantics and obstacle information. We convert CD joins into grid-based maps, where white cells represent accessible areas and black cells indicate obstacles like walls, globes, pre-embedded parts, and holes. Regarding the robot model, we simplify the robot prototype into 3 parts: the robot body, a tracked vehicle, the swimming arm, and the traveling disc. The geometry center of the tracked vehicle serves as the control point of the entire robot. It's important to know that the vehicle center and the swimming arm center may not coincide, and the robot's heading direction is the orientation of the tracked vehicle to avoid disturbing already traveled areas. Apart from basic geometry parameters, Accurately defining the position of the robot requires four parameters: x, y coordinates of robot control point, yaw of vehicle, and the swimming arm angle. Critical, we also define the collision principles of robots, containing two parts. For the tracked vehicle, we checked if obstacles are within its circumscribed circle and the rectangular area. For the swimming arm and disc, we judge the shortest distance from obstacles to the line segment, which includes the determination of three different regions. The collection area ultimately forms a capsule shape. The SatAOI algorithm is inspired by the BFS, Breadth First Search algorithm, since AOI presents the area reachable by the traveling disk. We use the disk as the main reference to search the entire map. The search process is the same as BFS, and OpenSat contains nodes to be explored, and the closed set includes nodes already visited. Among this flow, the most important part is collection judgment algorithm. In such algorithm, we traverse all angle placement situations of robots in a certain point. By considering discrete angle combinations of angle 1 and angle 2 at each node, with a step of pi over 12. If there is at least one pair of angles that keeps the robot collision free, the node is added to the open set. Overall on our methodology, then let's look at the results. We conducted a case study on a gas-insulated switchgear in a substation, which is full of columns, pre-embedded parts, and holes, and the geometric size of our robot model references a swimming arm traveling robot from Magic Beam. We tested three maps of different complexities: simple, medium, and complex, with obstacle area proportions of 3.49%, 7.46%, and 12.89% respectively. The AOI delimitation results can all competent, and the simple map test shows that the algorithm can fully consider regional connectivity of obstacle map. Based on accurate AOI delimitation, downstream tasks such as robot path planning and evaluation can be carried out, like developing AOI-based coast maps and path planning for traveling. In this research, we simplified and built mathematical models of the obstacle map and swimming arm robot, accurately defined the collision detection principle, and proposed the SatAOI algorithm for AOI delimitation, and using a case study proved its effectiveness in maps of different complexities. For future work, we are focused on the downstream application of AOI, including the cellular decomposition method based on AOI and developing AOI-based coverage path optimization and evaluation. Finally, I'd like to acknowledge the three funding sources for this research. And that's all. Thank you for your attention.